Thank you very much, and I would like to thank people for taking the time today to join Analog Devices talk titled Single Pair Ethernet, 10BASE-T1L Market and Technology Insights. My name is Maurice Brien. I am the Marketing Manager as part of Analog Devices Industrial Automation Business Unit, focused on condition-based monitoring and Ethernet connectivity. Michael, over to you.
And I'm Michael Brychta. I am System Applications Engineer with Analog Devices located in Limerick in Ireland. And my focus is on industrial communications and mainly Ethernet and mainly 10BASE-T1L recently.
So to briefly walk through the agenda as to what Michael and I will present today, I will kick off the presentation and I'll talk a little bit about the need for Ethernet and specifically single pair Ethernet. What megatrend is driving the need for Ethernet connectivity? And then I will introduce a little bit about what 10BASE-T1L is, how it compares to some of the existing communications technologies deployed in the factory today. I will also walk through some market insights. I will talk to potential deployments of 10BASE-T1L, why they are being used, and what value they will bring. And then I will pass over to Michael, who will talk about 10BASE-T1L, the technology itself, and he will walk through ADI's offerings and talk a little bit more technical requirements around 10BASE-T1L. Michael will also introduce POOD, which is power over data lines, or what is being called going forward in the context of industrial single pair PoE. So this is some new terminology that you will start to see. Michael will introduce POODLE / single pair PoE, and then finally I will wrap up and talk a little bit about the breadth of ADI's offering beyond 10BASE-T1L. So just to set the context a little bit around the need for Ethernet. The benefits of Industry 4.0 are really based around leveraging increased data for better decision making. Timely access to data and the delivery of that data throughout the automation system really hinges on the connectivity network. And networking technologies must evolve to really meet the demand for increased data. And with increased data come the capabilities and the opportunities to deploy more analytics, such that we can use more powerful analytics to ultimately drive significant productivity improvements and more flexible manufacturing. The challenge to date really has been in terms of delivering Ethernet to the last mile or to the field. And there has been challenges with it to deploy a long reach, higher data bandwidth connectivity to edge devices without the need for complex power hungry gateways, and 10BASE-T1L really finally solves this challenge. So a little introduction to 10BASE-T1L. So 10BASE-T1L was recently completed under the IEEE 802.3 standard on the 7th of November 2019. Analog Devices played a leading role in the development of this standard. One of my colleagues, Mick McCarthy, co-presented the original call for interest to justify this standard back in July of 2016. And both Mick and Michael, who's on the call here, would have helped the progression of the technical meetings along the way to its final completion in 2017. So 10BASE-T1L. So it is a single pair Ethernet media standard. It is 10 megabits. It is both power and data over the cable. Most importantly, it will utilize a single twisted pair cable. So we will move from the existing Cat5 cabling to a single twisted pair cable with 10BASE-T1L. It is a full duplex point-to-point communication, and it can transmit up to and beyond 1 kilometer. And specifically for the process industry, it is suitable for intrinsically safe, explosive safe, or sometimes referred to as hazardous area use case. So 10BASE-T1L can connect to devices that reside within zone 0 intrinsically safe. So let's take a moment to compare 10BASE-T1L against some of the traditional communications technology deployed in the process industry today. So we're looking at 4 to 20 milliampere HART, we're looking at field bus, and we're looking at 10BASE-T1L. We're going to look at data bandwidth, we're going to look at connectivity to the higher level Ethernet control network, ability to deliver power to the instrument, and the knowledge expertise associated with these technologies. So clearly 10BASE-T1L is a significant step in terms of increased data bandwidth when compared to 4 to 20 milliamp with HART at only 1.2 kilobits per second, or field bus up at 31.25 kilobits per second. So we have a much higher data bandwidth pipe with 10BASE-T1L. Really important with migrating to Ethernet is the move away from the more fragmented legacy communications that require complex gateways when they connect up to the higher level Ethernet control networks. And data islands have always been a challenge to date, where it's not always easy to access the data at the edge of the network. So by leveraging Ethernet, we remove the need for these complex power-hungry gateways, and we now get seamless Ethernet connectivity out to the edge to our sensors and actuators. Power is equally very important. So with 10BASE-T1L, we get significantly higher power capability, up to 500 milliwatts in zone 0 intrinsically safe, and potentially up to 60 watts in non-IS applications, cable dependent. So again, we've significantly more power versus 4 to 20 milliamp with HART, which is probably 36 milliwatts, and field bus has a little bit more power, but still significantly more power with 10BASE-T1L. And then finally, knowledge expertise can be a challenge with the legacy communications. As technicians and engineers retire and leave the workforce, it's becoming more difficult to bring in new talent that is familiar with these technologies in terms of 4 to 20 milliamp with HART and field bus. So Ethernet is very well positioned in terms of the available talent pool. Every college graduate coming out of college is familiar with Ethernet, and there also is the opportunity to tap into the talent pool from the IT infrastructure side, who, to be redeployed potentially into the OT environment. Briefly, let's look at how 10BASE-T1L compares with the existing, what I'll call standard Ethernet technologies today, 100BASE-TX and 1000BASE-T. So obviously 10BASE-T1L being a single pair Ethernet physical layer standard is really important when compared to the existing 2-pair and 4-pair Ethernet, because it opens up the potential to reuse existing installed field bus cabling. And that is a very important part of the 10BASE-T1L value proposition, is the potential to reuse existing cabling. Distance, obviously a significant increase, so we're no longer limited to 100 meters. We now can transmit up to and beyond 1 kilometer, which is a key requirement for delivering Ethernet to the edge in the industrial market. Speed is relatively low when we compare to 100 megabit fast Ethernet and gigabit, but again, coming from some of the legacy communications, 10 megabit is still a significant increase from those legacy communications. Single pair Ethernet can utilize a much smaller connector. So whereas standard Ethernet was within RJ45, single pair Ethernet now allows us to use a much smaller connector to connect to these new field devices. From a power delivery perspective and IS compatibility, so 10BASE-T, 100BASE-TX, and 1000BASE-T never could meet the requirements of intrinsically safe, given the high power, relative high power approach. They could never meet IS compatibility, whereas 10BASE-T1L can be deployed, as I mentioned, in zone 0 intrinsically safe. And from a power delivery perspective, standard Ethernet, typically obviously uses PoE, which needs a minimum of 2 pairs to transmit power. Single pair Ethernet will leverage POODLE, or as I said, single pair PoE, as it's beginning to be called, in more factory and building applications. And then we will continue to see engineered power being deployed for intrinsically safe hazardous area use cases. So let's take a moment to look at some of the key market trends and potential deployments for 10BASE-T1L. So the first one we look at is Ethernet APL. APL standing for the Advanced Physical Layer. which basically specifies the details of the application of Ethernet communication to sensors and actuators in hazardous area locations, and has been driven by a number of the leading process automation customers and will be published as part of an IEC specification. Ethernet APL will change the process automation world by enabling high bandwidth, seamless Ethernet connectivity to field devices. And fundamentally, it solves the challenges that to date have limited the use of Ethernet to field devices. These challenges are power, bandwidth, cabling, distance, and deployment within a hazardous area location. And by 10BASE-T1L and Ethernet APL solving these challenges for brownfield upgrades and new greenfield installations, Ethernet APL will enable new insights that previously were unavailable. And these new insights that will now be accessible across the converged IIoT network will open up the possibilities for advanced data analytics of the data. You provide more operational insights and ultimately drive productivity improvements through that converged Ethernet network. And as I said earlier, the higher power available through 10BASE-T1L in zone 0 really opens up the opportunity for newer types of sensors to be created that in the past would not have been achievable with the limited power delivery of, for example, 4 to 20 milliamp. So as we look to the right-hand side and we look at more of a network deployment of how 10BASE-T1L will be deployed by the process industry, the network topology here is what we refer to as a trunk and spur network. So at the control level, we will have a 10BASE-T1L power switch, which is where power will be provided to the cable. On the field level, we will have field switches, which will provide the device connectivity. The field switches will reside in zone 1, and they will be connected by what is referred to as the trunk connection, which can be up to a maximum of 1 kilometer. And then it's the devices, be it the sensors or the actuators that are actually located in zone 0 will be connected via the spurs, and the spur will be the connection from zone 1 into zone 0 for intrinsically safe applications, and the maximum spur distance is defined as 200 meters. This trunk and spur network topology really allows for a very scalable deployment. If we need to add more sensors or actuators to the network as we look to expand the process, then we simply add more field switches and have the ability to connect in more spurs. And Michael will talk a little bit more about some more details of this in his presentation. But ultimately, Ethernet APL will finally deliver seamless field-to-cloud connectivity for the process installation. Examples for the process would be, for example, food and beverage, pharmaceutical, oil and gas installations. And with this new rich data sets that will now be available across the converged IIoT network, it does open up the opportunities to potentially deploy more complex process manufacturing flows and ultimately create more value from these process flows. An important point that I would like to make around the transition towards 10BASE-T1L is that it will take a period of time. And what we're showing in this diagram is a transition from left to right. So on the left-hand side is the traditional approach where we use 4 to 20 milliamp connected devices. And Michael will talk a little bit more about the challenges with 4 to 20 milliamp in his talk in a few minutes. But what I'd like to focus on is the transition in the middle, where what we will see is we will start to see new devices that are utilizing up to 500 milliwatts of power capability to create new types of instruments. And these will be connected via 10BASE-T1L, but they will coexist and will reside alongside existing installed sensors, for example, that are connected via 4 to 20 milliamp. So we will see this dual deployment for quite a period of time. And Analog Devices has been investing in software configurable I/O that can be deployed in a remote I/O to provide more flexibility to support these existing 4 to 20 milliamp sensors and actuators by providing a single I/O channel that can be programmed to be analog in, analog out, digital in, digital out. So providing a lot more flexibility. And ultimately, these remote I/Os can then be connected up into the higher level Ethernet control network by either 10BASE-T1L or 100BASE-TX. And then As we move to the right, we see a future where we will get to seamless Ethernet connectivity, where all of the sensors and actuators will be connected via 10BASE-T1L. And analog devices, ADIN1100 or ultra-low power 10BASE-T1L PHY will be deployed at either the field switch on the infrastructure side or on the device side within the sensors and actuators to provide a 10BASE-T1L connectivity. Another interesting area and an emerging area is in condition-based monitoring. Condition-based monitoring applications continue to grow in importance as equipment manufacturers look to increase asset utilization with real-time monitoring of equipment. So they're looking to extend equipment lifetime, increase throughput by utilizing predictive maintenance techniques to reduce maintenance costs, and most importantly, reduced asset downtime. Condition monitoring is also used to improve the quality and the safety of equipment. Given the fact that unscheduled downtime can amount to nearly a quarter of the total manufacturing costs, predictive maintenance has the potential to unlock huge savings. And it's a key growth market. Industry market reports around condition monitoring are pointing to between 25 and 40% compounded annual growth rate over the next 5 years. So it's a really important area for Industry 4.0. It's a really strong growth area. And there is a great opportunity to deploy 10BASE-T1L in these applications to provide asset health feedback on a single twisted pair cable and providing both the power and data bandwidth connectivity. And I think the combination of both 10BASE-T1L physical layer with, for example, MQTT provides the combination where we got a messaging protocol for field assets with a very low memory footprint for very low power sensors, and that will provide us a means of getting that asset health insight directly onto a private server or up to the cloud for more advanced analytics and ultimately to deploy predictive maintenance offerings. So if you're interested in learning more about analog devices, complete system level offerings around condition-based monitoring, please look at analog.com/CBM. There was also an article published this morning, the timing was excellent, on Profi News, on an article that I wrote that talks in more detail to this specific use case. So please look that up if you'd like to see more about 10BASE-T1L in condition-based monitoring. Another key end market is building automation, and specifically intelligent building automation equally is looking to embrace single pair Ethernet. Here again, we see the breakdown of the control, the field, and the end node. Ethernet is deployed today at the higher level management control systems. At the control level, it may be 100 megabit, it may be gigabit, it may be fiber. And again, equally, as with the process industry, there is a desire to embrace Ethernet connectivity, to move away from the, particularly in building automation, extremely fragmented legacy communications technologies that are limited in terms of data bandwidth, have the interoperability challenges, and ultimately to date have been creating those data islands. So by leveraging 10BASE-T1L single pair Ethernet within intelligent buildings, in this example where we're looking at more of a HVAC application where the room controllers are being controlled by a 10BASE-T1L, higher value instruments or sensors and actuators are being connected via 10BASE-T1L at the edge of the network. But again, equally, we show that support that ADI is committed to in terms of that transition and that long-term support of the existing legacy communications, be it 4 to 20 milliamp, digital output, or just analog control via our software configurable technology. Other applications, broadly speaking, within intelligent buildings and automation, so beyond HVAC systems, IP cameras is another key area. So 10BASE-T1L with Poodle/single pair PoE will provide a means of connecting cameras over a much longer distance, up to and beyond 1 kilometer, without the need for leveraging fiber or without needing repeaters or switches connected. So I think the reach will become very useful for IP cameras. Equally, reach will be important for applications like building access controls. Fire safety is another application. We see customers wanting to deploy 10BASE-T1L because they need higher data bandwidth. They want to deliver higher fidelity audio commands in the event of an incident where they need to evacuate a building. They need higher data bandwidth for that. And finally, I guess the last example I talk about is elevators. So for example, the traveling cable. So the traveling cable is the cable connection between the carriage and the top of the elevator shaft, which often can be more than 100 meters. 10BASE-T1L is being deployed, potentially in elevator systems to provide that Ethernet connectivity and provide a high data bandwidth link between the carriage and the top of the elevator shaft via that traveling cable. So building automation will be a key driver of new 10BASE-T1L deployments. So now I will pass over to Michal, and over to you, Michal.
So check if you can hear me.
Yes.
Yes, so next. So I will talk a little bit about the context of the 10BASE-T1L. And I'll start with the process control use case, and deliberately because the process control was the one that drove the initiation of the 10BASE-T1L through the IEEE standardization. And I'd like to say that Analog Devices had been participating in the IEEE 802.3 CG that defines the 10BASE-T1L. One of my colleagues co-presented the call for interest in IEEE, which initiates the IEEE process of a standard. And a couple of my colleagues, including myself, are regularly participating in the IEEE meetings. And process control was one, or has been one of the use cases that has been driving the 10BASE-T1L. Now, it's not, as Maurice has already spoken about, lots of other applications, but the process control was the start of it. And why is it? On the picture, there is a picture of a typical installation in the process control. Today, most of the installations still are 4 to 20 milliamps analog loop. So it's analog communication from the sensors sitting on the edge of the process or actuators to the process controller. And as you can see, there is a lot of connections. So each sensor or each actuator goes by individual pair of wires from the sensor through junction boxes in the field, and then through sometimes very thick multi-core cables to what is called marshalling cabinet that rewires everything to the PLC, which has analog input cards, analog output cards. So there is quite a big mess in the wiring. So it's a very complex wiring. The principle is very simple. It's 4 to 20 milliamp from each node to input or output of the PLC. But with the scale, with the number of nodes in typical process, if we go to complex processes, and could be food industry, could be oil refinery, could be chemical industry, there is a large amount of nodes, and it makes it very complex with the scale. Imagine that you need to improve a little bit efficiency of the factory. You want to add few sensors, and now you have to find a way all the way from the sensor through those cabinets, through the wires, through the marshalling cabinet to add another node. And it's very difficult to manage. It's very difficult to maintain. So that's what makes it complex. And also it's very limited bandwidth, because 4 to 20 milliamp loops, again, which are dominant today, or even field buses in the industrial process control, foundation field bus, Profibus PA, these are limited to 31 kilobits per second. So it's very slow communication. And again, with the scale, with the number of sensors, and with the amount of information that is available on the end nodes, the bandwidth is very limiting. Then it came hard. Hard has been quite successful, but still, if you want to add hard communication on top of the 4 to 20 milliamp, some of the PLCs would not have hard in their I/O cards, So we'll be adding a hard multiplexer. You will add another complexity to the wiring. And hard, you would have to create a gateway before you can route the information up into the IT infrastructure and use some information from what is available in the sensors. What I like to mention is the intrinsically safety and explosive safety, more to say. Those sensors are very often sitting in dangerous environments, and it could be, as I said, or raffinery, chemical factory, it's obvious. But also, if you have a flour mill, the flour whirling in the air is also highly explosive. So there is a need for explosive safety. And next. So what we are leaning towards, or what our customer, the end user of the factory, are leaning towards, connect everything through Ethernet. So you can connect Ethernet. You can connect Ethernet through to PLC. Most of the PLCs to have Ethernet connectivity. You can connect it through switches. What makes difference to the 10BASE-T1L is that existing Ethernet could not be connecting to the explosive environments. It's simply too high energy. Also, in many of the factories, the distance 100 meter, which is the limit for the classical 10-100 gigabit Ethernet, 100 meter is too limiting. So 10BASE-T1L, when driven through IEEE, had few fundamental requirements. One was it has to work in the intrinsic safety, and the other is to cover the distance. And that's what drove, again, the definition of the 10BASE-T1L as it exists. And as you can see, going from the picture from the left-hand side to the right-hand side, it's the same sensors, actuators, sitting in the same potentially explosive, dangerous environment. It's connecting to through the same, as they call it, pores from individual sensors to the field switches. But anything above that is significantly simplified, because now you can connect the switches just with the same single pair Ethernet cable as the spurs. And then you can go to the power switch where you can inject the power for the sensors. So the whole structure can be powered from a single source, which again significantly simplifies the installation. And then it connects to PLC. Now, what the Ethernet brings a huge advantage is the data communication. The speed goes significantly up from 4 to 20 milliamp, which is only a couple of hertz, tens of hertz bandwidth, or even against the field bus, 31 kilobits. It goes to 10 megabits per second. And the other advantage is that because it's Ethernet, it's a standard Ethernet communication, there is no need for any gateways, for any translation. And on Ethernet, there can be coexistence of protocols. So PLC can control the process. PLC can get the control data from the sensors and control the actuators. And in parallel, on the same cable, because there is enough bandwidth, there could be another data channel, information channel from the sensors through all the switches and through the PLC and appropriate security gateways, but not translation gateways, just security. And you can get all the data from the sensors up to the cloud or any IT infrastructure that is appropriate. And that significantly improves potential for improving the factory efficiency and utilizing the data that is available in the sensors and use it as an information for optimizing the factories. And that's what's driving 10BASE-T1 in the process control. Next. And now we talk about what Analog Devices has an offer, immediate offer. We are sampling 10BASE-T1 PHY called ADI 1100. As I said, it's IEEE standard, so of course the PHY is compliant with the 10BASE-T1L IEEE standard. It supports the intrinsic safe applications by having the 1 volt peak-to-peak amplitude option. It can work from single supply 1.8 or 3.3 volts. Of course, if there is a higher amplitude 2.4 volt, then you need 3.3 volts power supply. With 1 volt, it can work from both. It has ultra low power consumption. It is very important. It is important in the industrial process control applications, again related to explosive safety, which can be realized as intrinsic safety. Intrinsic safety means that you limit the amount of energy that can ever get to the end node, and therefore that limited amount of energy cannot cause any dangers, any explosions. So that energy in the most dangerous zone zero equipment is limited to about 500 milliwatts that can go onto the cable. So there is some losses on the cable, so something above 400 milliwatts is available to the very end node. Then there is lots of protection. And then the about 39 milliwatt that is consumed by the PHY, by the interface itself, lower the power consumption of the PHY, more of that energy is left for the high quality sensor itself, and also for running the appropriate controller that extracts the data from the sensor and translates to the information and can run, as I said, maybe parallel protocols, the control protocol, and also could be running a web server or any other means of communications up to the OT operation technology or IT technology up the stream. And the low power, of course, will find attraction in other applications. If you imagine a building with hundreds, potentially thousands of sensors, each sensor pushing down the power towards low power saves energy, saves copper in the wiring, and therefore low power is very important for any of the applications. So the 10BASE-T1L PHY is sampling now. It is in a small package, and it is indeed in the industrial temperature range, can operate in the industrial temperature range. And any details you can find on our website. You can see the link there. There is preliminary data sheet, and we will be feeding more and more information about the PHY and its application there. Next. So here we can see the PHY in context of the application. It's a PHY, so it has a standard MAC interface, MII, RMII, RGMII going forward. It is clocking from a standard 25 megahertz oscillator or crystal as any other PHY. In the case of RMI interface, it needs 50 megahertz clock. And then it has all the modes, 1 volt peak-to-peak operation, 2.4 volt peak-to-peak operation, master slave, and it has auto negotiation. I would like to highlight that the auto negotiation is desired and preferred mode of operation for any PHY, because that's what makes the Ethernet as we know it from the offices or any infrastructure successful. It's auto negotiation. So right now it decides what is the amplitude. If one of the nodes is sitting in the dangerous environment and connects even to some other application that is capable of running 2.4 volt amplitude, it can still tell, hey, I can work only 1 volt. The other side accepts it, and they agree on cooperating 1 volt. You don't need to care about which side should be master, which side should be slave. So you can daisy chain the switches. Auto negotiation is definitely an appropriate way of operating any Ethernet where auto negotiation is possible. And then the PHY not only fulfills the IEEE requirements, but includes some diagnostics. There is on-chip frame generator and checker, which significantly improves the possibilities of debugging the design of the system and deployment of the system, has multiple loopbacks modes. Of course, it includes all the IEEE mandated test modes. and include some other test modes that improve capability of the cable diagnostics. Next. And as with any of our products, we not only offer you the chip, we also have evaluation boards for the part, so you can get an evaluation board. We have a graphical interface for the evaluation boards, little piece of software, so you can play with the PHY registers, with the diagnostics. You can set it to different modes, and you can connect it through, there is an FMC connector on the bottom of the board, which is a standard for connecting to some FPGA platforms or microcontroller platforms. There's also a header. So you can use it as a starting point. You can play with the cable, you can play with the PHY, and you can connect it as a prototype to your existing system and play with it as a system. And you can check the performance. And we are also checking the EMC performance. So you can see the list of the industrial standards. So it's a system, there are system level tests. And because there are system level tests, we don't test them on the chip itself, but we test them on this very application board, as you can see it. So on this board, we performed all these tests. Next. So we talk a little bit about the power over data line single pair power over Ethernet. So it is, again, there are a couple of approaches here. One is it can work according to the IEEE standard. There is IEEE standard 802.3 BU, which is that single pair power over Ethernet. There is also the 802.3 CG addendum for the 10BASE-T1L, again includes the appropriate power classes for the 10BASE-T1L. So you can see that the power delivery can go up to about 50 watts of power over the single pair Ethernet with 10BASE-T1L. By principle, it is very simple. The data is AC coupled. You can see the data go from host 1 to host 2 through the PHYs on both sides, and AC coupled. Here is shown through capacitors. It can also couple via transformer if and where appropriate. And then the power is coupling from the power sourcing side, which is called power sourcing equipment, PSE. So it's pool PSE, and it couples through inductor, differential inductor, to the line. And on the other side, it's extracted back from the line, again through an inductor and through a PD power device. So in this example, it's classified power, which means that the PSE and PD side can communicate to each other. So when you plug in a device, there is another communication which is outside normal Ethernet frame. It's not Ethernet communication through the Ethernet frames, but there is a specific IEEE defined communication between PSE and PD. The PD will tell the PSE that it is there, and it is safe for PSE to apply the power to the cable, and how much power PD is requiring, and what voltage the PD can accept. And if they agree that they are compatible, the PSE will apply the power to the cable. It powers up the system on the power device side, and only after that will assume the communication over the Ethernet. This is a standard mechanism that has been deployed for a long time as the power over Ethernet, and it is replicated here as the single pair power over Ethernet. And then, of course, applications like I mentioned before, the process control. There is no negotiation about power, because if it's intrinsic safe equipment sitting in the most dangerous zone 0, mixture of some very dangerous explosive like hydrogen or some mixture of some petrochemical material, there is no negotiation. In these applications, there will be engineered power. The principle would be the same type of coupling, but around the coupling indeed has to be lots of protection components, and there is no negotiation. The power on the PSC side is limited by what normally in the industry is called intrinsic safe barrier. Next, and not to mention the PSC and PD side, analog devices is working on chip solutions for the PSC and PD for the power over single pair Ethernet. And when we talk about tools, we also have some demo boards. This is a demo board that combines the 10BASE-T1L and power. So you can see it translates 10BASE-T1L Ethernet. And here we can see the board accommodates a footprint for Harting connector. So you can see Harting connector and mating with Harting connector on the cable, which is complementary. The process control industry will use screw terminals, and that's what they want to use. The rest of the world will probably use connectors. So the yellow cable from the left-hand side carries on the 10BASE-T1L and power. The connector on the right-hand side is the standard RJ45 connector for Ethernet. And on the board, there is translation between those two physical layers. And also the board is capable of injecting the power to the cable. There is no connection shown here, but from the black bar connector on the top or one of the green connectors, you can apply power and the power is coupled to the cable. And that's all I had, I think.
Thank you, Michael. And just to briefly mention some other material that's available, if you'd like to read more about 10BASE-T1L, there are a number of articles on analog.com. Equally, you will see some articles published on Profi News, and there are a number of videos also on analog.com. So my last slide to summarize, 10BASE-T1L single pair Ethernet solves the challenge of a long reach industrial Ethernet physical layer to the field, or sometimes as we call it, to the edge, and will ultimately allow the deployment of a converged IIoT network across industries such as the process, factory, condition monitoring, to ultimately allow more access to data, which ultimately will allow us to improve the flexibility, the quality, and the scalability of our manufacturing capabilities. If you would like to learn more about Analog Devices Industrial Ethernet Solutions, please visit www.com/Cronus, and there you will see ADI's offerings for physical layer devices, embedded switches, and platform solutions. And with that, I will hand back to Matthias. And thank you all for your time today.
Yes, thanks. I'm back here. And I think we have also some more questions coming up here in these different sessions. And I'm looking around. So as first of all, thanks for all this detailed information and all the details you share with us. Okay, one question come up is regarding the function of the T1L switches we see in the applications for the process industry, this trunk switches and this power switches. You can go back to these pages, and somebody wants to know what are the real function. I already described it a little bit in a way that these are concentration points, but also they have the function to power some. I think it was, yeah, this page where you have the switches in the different levels, and some of them offering powers and some not. So here the question was,
okay, so I guess it's a more technical question, so I take this up. So from the Ethernet point of view, it doesn't make any difference. There are switches, Ethernet switches that switch the packets. So if the packet is meant for the sensor, it routes it to the sensor. It's not meant for the sensor, it routes it to other switch. So it's normal Ethernet switch as would be any other infrastructure Ethernet switches. When it's called field switch, the field switch is sitting in the field. So the field switch, along with the Ethernet switching. It also redistributes power, so it can be powered from the trunk. So it can take the power in from the trunk and can distribute the power to individual sensors. And when distributing the power, if the field switch is for the process control, for those dangerous environment, it also performs the function of limiting the power to the safe level for the environment that is sitting at the edge of the process. So field switch is redistributing the power. Power switch is injecting the power to the network. So
Yes.
it's more naming from the power perspective, specifically in the process industry. From the Ethernet point of view, it's a normal Ethernet switch and there is no difference between them.
Yeah. Thanks for this detailed explanation. Here's another question coming up. I think it's related also to the difference and the understanding what is APL and what is single pair Ethernet and what is PUDL. So the question is, APL is working without PUDL, but I see power profile. Isn't that easier to maintain over time when engineering of PUDL? What is the value of the user? But we see it already in the presentation today in the morning coming from Entrus and Hauser, where there was a very nice table inside where they compare APL and PUDL. So APL using this 10BASE-T1L standard for communication, but they have different power profiles compared to PUDL. And this is the main difference. And the power profiles from APL are for intrinsic safe and PUDL not support intrinsic safe. So that's the main difference.
So Matthias, it sounds like already answered the question.
Thank you, Michal.
So,
that was a great answer.
Yeah,
yep.
okay. So, some more I have to look around. Here's a nice. I think it's also answered already a little bit, but you can go into. At the beginning, somebody asked when the RDE N1100 will be available, but you say it already, it's ready for purchase. Is this evaluation board also available?
Yes, so Analog Devices is sampling the ADI N1100 today. So both loose samples, the product applications board that Michael mentioned that we've done all our EMC testing on, and we're also sampling the media converter board that again Michael showed that will provide the media translation from 10BASE-T to 10BASE-T1L that featured the Harting cable and connector. So I would say please reach out to your local Analog Devices office or to your local ADI franchise distributor if you would like to get any loose samples or applications boards. And the specification in terms of the data sheet is posted to analog.com. So yes.
This is very good. And I think it's also related to another question come up. When you expect to see devices and equipment using this technology. So what do you mean for this?
Yeah, okay, so it sounds like when do we expect to see 10BASE-T1L enabled equipment, I guess, becoming available? So I would say in the second half of next year, so second half of FY21, we expect to see 10BASE-T1L enabled equipment becoming available. And I think more specifically, we are looking to the ACHIMA trade show next June. Obviously, that's a very important process automation fair. It only happens every 3 years. And we expect that, particularly the leading members of the Ethernet APL grouping will be, demonstrating and introducing their 10BASE-T1L enabled equipment. So,
yeah, this fits also to the presentation Entrus and Hauser show up in the morning where they describe also his use cases for the process industry and expect the same. And they mentioned also from the APL use case that many other companies also like Pepper and Fuchs, Rockwell, and so on, working on this, and everything's showing up at the next fair. Yeah, I think it's more or less everything. That's a small comment also to the demo board where you show up besides the terminal blocks, also the interface from us. And somebody mentioned, of course, this is right, the connector we offering is not fitting for the applications you have for intrinsic safe, is clear. But you show also that 10BASE-T1L is not only, the 10BASE-T1L is not only APL, it's also many other use cases in building automation.
Factory automation, the condition-based monitoring. There are lots of applications that what we would say is, they're used to Ethernet, they're used to plug and play, they're used to connectors, and they expect a connector. So for factory, building, condition-based monitoring, we expect that we will again provide them with plug and play solutions, and they will continue to use connectors. The key difference being now the connector is much smaller with single pair Ethernet.
Yeah, and definitely for other use cases beside explosives, atmospheres, connectors are used today, and that's why the standard was established, what we're discussing a lot. Here another question come up, but it's can we power sensors using SPE with POA? I think we can answer this all together. POA uses pairs for distributing the power, and that's why for single pair Ethernet we need power over data line using the 2 wires we have. So this is the answer for this colleague. Okay, I think we got the most of the question. If some other special questions come up, also here the invitation, please go in contact with Analog Devices and you get support from you, of course. And thanks so far.
And finally, I would like to just thank the single pair Ethernet grouping for inviting Analog Devices to present today. Thank you.
It's also a great pleasure for your presentation, and I like to see you in this way because since the last time we see you as regular at the IEEE meeting, and now everything is analog. So not. So we have to do all these presentations with video. Hopefully we will see us next year again.
Yes, hopefully at the next trade show or next in-person event.
Yeah, thanks so far here. I see already Thomas is joining from Texas Instruments, the next presentation. But we have more or less we can have a short break with the intro for your presentation, and we can continue directly. Yeah.